Hello everyone. In this tutorial, we'll start Abacus training or Abacus modeling of one of my article which I published this year. This article, as you can see here, is in ocean engineering. I will put the link of this article in the description of for this video. However, you can see this article is about numerical modeling of suction Caisson on under monotonic lateral loads. So I have opened the PDF on the other side. I'll show you what this article is about. So basically we looked upon one of the literature, which is Lee et al 2014. You can again check it out here. It was one article from Applied Oceans Research, and I use this article to basically model this as you can see, this drawing is in 2D, but I'll show you in 3D what we did. So we modeled a Caisson, and then there was another Caisson. So I'll just show you one of the model. So you can see what we did in Abacus was that we created the laboratory setup as Abacus model, and this model was simulated under lateral loads, and the properties and everything else is given in this tutorial. I am currently going to show you how the implicit model took place, was modeled in Abacus, was simulated, and how the results look like. Results are also shown in this article, as you can see. So I have named but bit weirdly, but the article is now published, so it's accepted in the research community, so you can check it out. Now coming back to Abacus, I have created a ABAQUS-Python script. With this ABAQUS-Python script, I can basically run a script, and this will create all the models which we want. So I will also put the script in GitHub repository, where I will for which I will share the link in the description of this YouTube tutorial. So what this script, ABAQUS-Python script did is that it created 4 models. Those were not here before. And to show you the model, I will go into this model M2S1A, and I'll also show you what M2S1A means. But basically A, B, C and D, this represent the changing scenario of skirt. I have to deselect. So this is a, I don't know how to, yeah, sorry. Yeah, let me go to another model and then come back here now. Yeah, so you can see that there are 2 major parts of the model. I'll show you in the assembly, which I have also showed you in the paper research article which we have published, that there are this sand. I'll go to material properties, like materials basically. Now you can see the red one is the steel part, which is representative of suction Caisson. Overall, this research represents how if we create a windmill, if we build or construct a windmill in the sea on the top of a suction Caisson, which is like a well foundation, how will it perform under lateral load. Lateral loads are representative of wind loads. When winds hit the turbines, they force some lateral direction movement of the overall pole of the windmill. So this rod here, it represents the pole of that windmill. We haven't created the actual turbines here. The lid is basically the cap of the pile or cap of the bucket foundation or the well foundation. Then there is the Caisson or the depth of the whale. So here it's a bit complex because we have one skirt here as well, which is another Caisson outside of the main Caisson. So coming back to the Abacus, our code, what it does is that it creates 4 models: M2S1A, M2S1B, M2S1C and D. In all this model, the only thing which changes again is this part, which is the Caisson all. So it's a composite part. It contains the foundation, which is made up of concrete, the top part, which is made up of the foundation is made up of steel, but in general you can also make it out of concrete. The top part, which is generally made out of steel, because in offshore applications we generally don't construct like we try not to construct with concrete mostly, but it depends. In onshore also you have seen windmills, like on land windmills which are completely made out of steel frames. So coming back from A to B and C and D, I'll show you what's the difference between this Caisson all. As you can see with in A we didn't had this skirt, but in B we had this skirt and it has some specific length. In C, the length of this skirt is it keeps on increasing. So you can see this length has been increased. Again, going to D, this length will further increase, and you can see this, the visual proofs are all here. Now going back to the mesh. To build the mesh, what we did was that we had to create several partition, because without partitions it's almost impossible to have proper mesh. And just to show you in loading diagram where we can see the partition, also in assembly you can see overall partitions, how we have created partitions. Now there are several questions which people might ask: why don't you create why haven't you created cylindrical sand and gravelly strata? So I'll show you again. This model is basically based on this experimental setup which is adopted from Lee et al. They have created a rectangular tank, and in the rectangular tank they have filled the upper part with sand, the lower part with gravel, just to allow drainage. The whole condition was wet, but we didn't use wet condition. We used kind of dry condition. Also we used some part where we applied saturation, but it doesn't affect much. So coming back to the abacus part, now you are familiar with internal Caisson, external Caisson. Now I'm going to show you the script which we have run. This is the script, and I'm going to open this in Notepad++. So this script I have put previous tutorial using which you can run abacus macros, and we have created this script using abacus macros. One of our paper is going to be soon presented in a conference in Vietnam, and there the first author of this article which we have published will present it. But just to show you this, that we have created 4 model names. As you can see here, all the upper parts are commented out, but I want to show you the first 4 comments which describe what are the properties of this Python abacus Python code. All the values are in meter, kilogram and seconds. The basic unit description which I should give you as a disclaimer: M1, M2 and M3, S1, S2 and ABCD, which will look further, and then will go back up. There is a parameter. These are the parameters which we need to define. M1 defines the length or depth of initial or first Caisson. So there are 2 Caissons, one is internal, one is external. External Caisson is generally called skirt because it looks like a skirt, which is a girl clothing item which is worn outside of the main under garments. But yeah, it's let's not go into that. But the thing is, M1 represents L1, S1 or S2 represents D2, A, B, C, D represents L2. So we change these values based on what the model name is. So if the model name is, for example, M2, S1 and C, M2 will go to this else part, because it will skip if M1 is equal to M1 ni, M3 ni, which is not the part. It will go to else, and the L1 value will become 0.24 negative, because we are pushing extrusion downwards. That's why we are taking negative values. Then S1, if we detect S1 value in the name of the model, then we put D2 value as 0.3, again negative because we are pushing downward. Then A, B or C, D, if for most of them we have A, B and C, D, all of them. So you can check if it's A in the name of the model, the L2 is 0. Now let's get back to what are L1, L2 and D2. So these 3 lines, as you can see, there are 3 parts: internal Caisson or first Caisson. M1, M2 and M3 are deciding factors for the depth of first Caisson. So we have basically kept it constant because we have taken M2 throughout the throughout the models, all the models, the m2 is the name of m2 is constant, s1 is also constant, so m2 and s1 are constant. Again, uh, s1 and s2, it represent the diameter of second Caisson. So diameter of the skirt or outside Caisson is also constant, but a, b and cd are changing, and a, b and cd are the depth of second Caisson which are changing here. So coming back to the bottom of this model, you can see that based on this we have to create some other parameters which we might need to we can also assign this in the name of the model, but I have created for the simplicity. And in the future works we have started doing more and more automation, so that our whole model name will be a bit longer, but everything will be automated. Again, diameter of Caisson, which is fixed, because the internal diameter Caisson of diameter of internal Caisson, we have fixed it to 0.6 meters. And the thickness here is the thickness of the Caisson wall. So here this Caisson thickness is fixed, and according to code it's 0.02 or 0.002, and then there is thickness of lid. I'll show you what is the thickness of lid. So here you can see the thickness of lid, which is the thickness of a cap. You can call it you might have you might like to relate it with pile caps or bucket caps or any caps which we put on the top of any hollow foundation, just so that we can land on it anything, or we can build over the top of it. So this is the kind of lid thickness. So these are the parameters which we define, and then based on that we run some other loops. These loops are basically recorded data. When we keep running this exercise over and over, every part which we create in the abacus, we keep running as we keep recording the macros, and each macro we collect and we merge all the macros together. So we create sketches like this, and we keep on going. So we have sketches as we have changed the name and rod revolution. So we have named sketch like int Caisson, which is internal Caisson, and Caisson lid, which is internal Caisson's lid, and RVL, which represents revolution. So some of the sketches will be converted into parts via revolution, which I'll show you in the future, and some of them will be converted into parts via extrusion. So we have created the name nomenclature such as XTR and RVL at the end, and you can see that. And there are specific construction line and fixed constraint associated with the revolution sketches, which are not given in extrusion, because in extrusion you don't need to provide these things, because the rotation takes around the construction line, and the construction line is kind of fixed. I would say it is fixed. Then the parts are created for revolution by rotating the sketches 360 degrees, and the further explanation I have provided in the comments here. I haven't provided explanation for every line or every other part, but you can understand it. It is pretty simple English based Python ABAQUS-Python codes. Base solid revolve, the angle is 360 degrees, flip revolution direction off if we are not flipping the direction, and anyway 360 degree if we flip or not, it doesn't matter because we are completely rotating it. Then the sketch name goes like MDB model name sketch I, because we are running the loop over all the sketches which have revolution underscore RVL in their name, if RVL and I. Similarly, for extrusion sketches, we have two of the sketches, and we have to define the extrusion depth, because the gravel and sand have different depths, and we have to define the extrusion depth here. Look, extrusion depth. So we create loops. Similarly, this whole code goes down, and there are several complex structures of the code where when we create partition, we have to create sets, we have to create surfaces. All this things goes down, and you can create repeatability, reproducibility of the code. There are several parts which I would like to cover here. As you can see, we can also put kind of debug arguments if you want to see when we run the code. There is some printing argument. If there are some error false before this, or something doesn't go after specific code, we can just print. These are debug arguments. We can, if you study Python, you will understand that for a code to run, if you want to see where the code stops to run, you can just print something to see. Until that print, the code is running or not. So this is kind of a debug. We check how far our code goes, and then we create assembly at the end. This is basically for all the parts. We run a code which creates their instance into the assembly, and A is basically root assembly, and then we keep doing it. Then there is rotation of several parts, which are sand extrusion, gravel extrusion. Then there is translation of gravel extrusion and sand extrusion, where the Caisson is. Also, what we did here is that we have to merge all the parts like internal Caisson, revolution, lid, rod, and then we create steel all. There is a list, and then what we do is that we instance from boolean merge. We merge all the Caisson parts which are here. A dot instance I for I in steel all. Steel all are the parts where we have sand, we don't have sand or gravel. So whatever parts, if their name doesn't have sand or gravel, we create a list of all the parts, and then we merge them, and then we cut the sand part using Caisson all part. So you see, this will create a new part, but we have to delete the sand extrusion part, which was the original sand part. So in the end, we land with two parts, which is Caisson all and sand all, which I can show you again in the abacus module. So we go to parts, and we have this Caisson all part and this sand all part. Again, let me go back deeper into assembly so that you can also see. In the instance, we have three. Gravel extrusion, which was, we didn't do anything, but Caisson all, we merged the Caisson all, and sand all, we basically cut the actual sand extrusion part with the Caisson all part. Going to assembly, you can also see it here, the red one, and so on. So we are in D, but yeah, let's go here and we can see these parts. So this is the basic explanation. Then there are boundary conditions and loading and material properties. So we create material properties like this, elastic materials such as steel, sand, gravel. Initially we create every material as elastic. Later on we provide cohesive more column property, basically frictional more column property, but we provide some cohesion because we don't want our model to basically give plastic deformation right away. We want it to run for some time and then give some plastic deformation later on. And then we provide more column material property to sand and gravel, while defining phi sand, phi gravel, and cohesion. Also we kept cohesion for sand and gravel 500, which is a dummy value, which you can also assume. Then we go to home section creations. We create homogeneous sections, 3D sections. Then again there are assignments, section assignments based on if there are partitions or not, but I'm going to just skip it. It's a bit complex for this part of tutorial, but yeah. Then we create mesh. We have created sand all, Caisson all, extrusion all. We have assigned different mesh sizes, but you can use same mesh sizes and skip some of the lines of this code. But basically we wanted to have this C3D8P, which is porous stress plus porous elastic mesh, because this is an implicit analysis and we are trying to use soils and geostatic steps. So we have to create such mesh, and you can see we have created a geostatic steps and then soil step, and then we have requested field and history output in those steps. Going back, we have created a fixed boundary condition, which is at the bottom, roller boundary conditions, which is on the sides, and then basically this if there are several parts like extrusion and sand all, then we merge the part and apply roller boundary condition. After this we applied pore water pressure condition. Everything is basically commented here in the codes. If skirt, if no skirt, there are different conditions. Then there is a friction between the Caisson and the sand, in which, because we have inserted the Caisson in the sand part, so that's how it is. And then we have created this friction condition and applied it to the sand and Caisson. Going further down, we have applied the loading condition, but before that we had to apply the void ratio. This is a bit weird here, but uh, for A at the root assembly, this we I actually deactivated geostatic stress because it was affecting the model, but you can also use geostatic stress. But the thing is, we have applied gravity instead of geostatic stress, so whatever suits you. Then we have created load increments. Basically, you can change this in the this sort of simulations, how much load you want to apply, but it's all based on what Lee et al did in their simulations. So we copied what they did as experiment and we applied the similar loading increment and loading condition, and then we created a job and then we ran the job. So that's how we came to do all the load. Here you can see we have created gravity and point load instead of geostatic stress. You can do that. You can go to instead of going to mesh, other parts again I can show you in the fixed, which is the bottom part, as you can see this, which is fixed, and showing you the roller part, which is all the sides are roller. So it's not that complex. And the load, which is the point load, I'm going to just show you. It's at a point. So I have created 4 partitions. This study, so Lee et al, this studies several aspects like eccentricity of load, the diameters were different, but we took one specific part for our validation and then we ran with it and the validation was successful. So I'm just going to dismiss it, and I'll show you once again the research article here, which we published, and the validation, which went pretty smooth, I would say. And you can see this M2S1A, M2S1B, M2S1C, M2S1C. So we collected the experimental results from Lee et al and we compared them with the simulation results which we did. The black line here is explicit FEM, red line is implicit FEM, and green line is the experimental data from Lee et al. The thing is, the red line doesn't go all the way up in most of the simulations, because in implicit simulations, the model with minimum cohesion generally fails. It doesn't go through. But in sand, we cannot provide any friction because it's not like that. So we have to go ahead and provide some friction, but it's a limit because we want it to be truthful to the actual nature of sand and gravels, which doesn't have any, both of them don't have any friction. And yeah, these are the results we provided. Later on we changed the code for our own understanding, but in this tutorial we'll just cover the implicit code, and I'll upload the YouTube video with the description of all the articles, all the GitHub codes which I have created. So I guess that's it. And if you have any questions regarding these publications, if you want to follow up, if you want to learn something, you can just hit me up, and hopefully I will try to do better tutorials. But for the sake of less time, I am just finishing this tutorial here. Thank you.